Now, in this tutorial, I want us to look at what we mean by a principal argument. And we're going to start by looking at the definition of a principal argument. And we're going to say that a principal argument is a value of theta which satisfies the following conditions. So we're going to say principal argument is the value of theta which satisfies the following conditions. One of it is that this theta that we are talking about, and theta is the argument of a complex number, is actually going to be greater than negative pi, less than or equal to pi. So which means that this also can be given in degrees, which means it can be given as theta is greater than negative 180 pi degrees, less than or equal to 180 degrees. This is one of the conditions which a complex number has to satisfy for it to be a principal argument. This is very important because most of the time you find that it's quite confusing to students. Let's look at another format it can be given is that this theta that we are talking about is greater than 0, less than or equal to 2 pi. It can also be given within this range, and this is actually in degrees. This is theta greater than 0, less than or equal to 360 degrees. So anytime you are trying to work out a question and then you are supposed to give the principal argument, then you must ensure that it's within this given range. That's the first condition. Now, the argument that we are talking about in this case, of course, this is the imaginary mz, and this axis here is the real z. So if we are talking about the argument of a complex number, suppose we have a complex number which has x and it has y. So in a Cartesian plane, we are going to have this complex number represented as such. So meaning that we have our x and we have our y, and then we have our x at that given point. So if we have our x at this given point. So meaning this angle that is measured anti-clockwise, the angle that is measured anti-clockwise from the real axis is the one that we call now the argument of this complex number. So if this argument, this angle that we are talking about here, is within this range between negative 180 and 180, or between negative theta and theta, or between 0 and 2 pi, then now that angle qualifies to be the principal argument. Then now, in order to find this angle, remember we can be able to use SOHCAHTOA. This is the part that you learned trigonometry year 8. That's where it was introduced. Then we're going to say, therefore, in order to find this, we have this is actually, this is opposite. Let me just write opposite, and this is equivalent to adjacent. Then you can see now the part we are going to use in order to work out that angle is tan. So we can say, therefore, tan theta is equal to opposite over adjacent, which implies that the angle theta is going to be equivalent to tan inverse of y over x. That's how we usually calculate the angle of the argument of a complex number. But in this case, I'm going to use a different value because theta has been unanimously been used here, theta to imply an argument, principal argument. We are going to use another letter. We are going to use alpha to be the angle, of interest, because we are going to use theta to represent the principal argument. Now, in this case, when we shall be working out this question, we shall referring that to actually alpha. So I'm going to illustrate that, what I mean by that. So let me start by working out the first the first example. We are told find the modulus and principal argument of the following. So number one, we are trying to find, or we are trying to work out the modulus and principal argument of a complex number which is in the first quadrant, because a complex number can be in the first quadrant, can be in the second quadrant, can be in the third or in the fourth quadrant. So we're going to see what we mean by that. You have z is equal to 3 plus 4y, plus 4i. So this is a complex number which is actually this is a complex number which has the real part 3 and the imaginary part 4. So meaning that in the Argand diagram, this can be represented as follows. We are going to say on the Argand diagram, that's going to be actually the MZ. We have the real Z, and we have the origin. So meaning that on the imaginary part, we have 4. On the real part, we have 3. So meaning this point represent that complex number there. So we can be able to join through the origin like that. And then we shall have our angle theta to be that. In that case, can see that alpha equals to theta. So I can say this angle I'm finding is actually alpha, but in the first quadrant, the angle you get alpha represent the principal argument. This represent the principal argument. So that one will not give us problems, because we know that first we need to find the modulus, and the modulus of z is actually represented by r, or like that. Modulus of z is actually represented by z like this, or r. Yeah, so this one here is actually r, which is the modulus of this complex number. So r equals to modulus of z, which is going to be equal to the, so this is actually at this point here, you can see we are having 3, and here we are having 4. So this is 3 and this is 4. So meaning this is 3 squared plus 4 squared, which is going to translate to 9 plus 16, and that is root 25. So meaning that the modulus of this is actually 5. The modulus is 5. So the next part that we need to work out is the angle theta, and alpha, this angle alpha is actually tan inverse of y over x. And in that case, we are going to say now we have worked out the first part of finding the modulus. And the second part that we need to work out is alpha, which is the argument, which is actually tan inverse of y, which is 4 over x, which is 3. And I'm going to work out my answer in radians. So if I work this in radians, let me see what I'm getting. So this is a tan inverse 4 over 3. If I work out that, I'm getting this value 0.927. So this value here is 0.927 radians. So in that case, whenever you can see now this value you have here is between 0 and 2 pi. This value is between 0 and 2 pi, or is between negative pi and pi. So this becomes, it qualifies to be the principal argument, because all angles, all complex numbers which are in the first quadrant, the value get, so long as the complex number is within the first quadrant, the angle you have is the angle. If you calculate the alpha angle, the alpha, it becomes automatically the principal argument. But that's not going to be the case when we are going to have a complex number in the second quadrant. In the second quadrant, let's see whether we can have an example which will take us into the second quadrant. Yeah, let me have an example that will take us into the second quadrant and try to squeeze that. So we have a complex number which is like, let me just, z equals to minus 5 plus 3i, minus 5 plus 3i. So you can see, if you try to plot this point, is this complex number on the Argand diagram, you are going to have it here. This is minus 5, and then we have, can say our 3 is at this point. So this number is in the second, quadrant. Oh, just draw it first. Now you can see now this complex number z here is in the second quadrant, which means that the angle alpha that we are working out, the angle between the line joining from the origin to the point of the complex number, this is the alpha that we are talking about. So our alpha is actually at this given point. So meaning here we have 3 and here we have negative 5. So in order to work out the modulus of z, this is going to be square root of negative 5 squared plus 3 squared. If you work out this is going to be 25 plus 9. Then the square root of that is going to be root of 34. So the modulus of this complex number is root 34. Yeah, the modulus of this complex number is actually root 34. But what about the angle at this given point? What about the angle at this point? So long as you remember this concept, I need to remind you that alpha is going to be the tan inverse of 3 over 5. Yeah, 3 over 5. I'm not going to put into consideration the sign that I'm having there, because I remember exactly what I'm going to do. Yeah, I remember exactly what I'm going to do in that case. So which means that if I ignore the sign of 5, but I know in which quadrant this is going to be, yeah, I want you just to understand it that way, that you can ignore the 5, but you know exactly in which quadrant that is. Then if I work it out, I'm getting, actually the value I'm getting here is 0.684. 0.684. Now, this is the value of alpha. But now, in which quadrant is it? It's in the second quadrant. So, which means, how are we going to get the principal argument? The principal argument is usually measured from the positive real axis in the anti-clockwise direction. So which angle is this? Which angle is this? Because all along this line we have 180 degrees, which is equivalent to pi radians. So meaning that for us to get this angle that is remaining in this section here, we are going to say pi minus alpha, pi minus this angle that you have here, pi minus this angle that we have at this given point, pi minus this angle that we have here. That's why I wrote that in the second quadrant, the principal argument is going to be obtained by pi minus the angle that you will get. And that's why you saw I ignored these 5. So we are going to say the principal argument in that case is going to be pi minus 0.684. So if I put that in my calculator, pi minus 0.64, 0.684, I'm going to get this value 2.457. If I round off, it becomes 2.458. 2.458. This becomes 2.458 as in radians as the principal argument in this case. So the most important thing whenever you are told to work out the principal argument, you need to ask yourself in which quadrant it is it. Then that, and remember the angle is measured anti-clockwise. So if we are going to have a scenario, whereby you are to work out a question that is in the third quadrant down here. It means we are going to let me see if we have a question that is in the third quadrant. We just erase this because at least we have made use of it. We appreciate it. So I want us to work out the principal argument for this number, minus 3 minus 5i. This number is basically this number is basically in the third quadrant. So if you put it in the Argand diagram, you realize that this is the MZ, this is the RZ, and then if we are plotting -3 will be here, and then -5 will be at this particular point. So we can say, me draw it properly, 3, and then let me just say -5 is at that given point. So you can see the angle alpha will come here. Our alpha will be at this given point. So first we need to work out the value of alpha. Okay, because we want to work out the modulus, and then we work out the argument. Let's say modulus of z is going to be square root of -3 squared plus -5 squared, and that is going to be square root of actually 9 plus 25, and basically this is going to be root 34 in that case. But alpha angle is going to be tan inverse. I've just told you, you can ignore the negative that we are having here, you know where that is, because this is actually going to be 5 and this is going to be 3. And then I work it out as 5 over 3. If I work it out using calculator in radians, I'm going to have what? I'm going to have shift tan inverse of 5 over 3. If I work it out, let me see the mistake. Yeah. I'm getting 1.03. 1.03. So, in order to state the principal argument, remember it's pi plus alpha. And how are we getting this pi plus alpha? We are going to move up to this point. We have pi. Then we shall produce, we add the alpha that was at this given point, because the angle that is formed right from the positive part of the real axis is going to be equivalent to, so theta is going to be alpha, which is 1.03 plus pi. So if you work it out, if I add my pi this given point, I'm going to have 4.17. This is 4.17. So basically, that's what you do when you are finding the principal argument of complex numbers. So something else maybe I need to mention here. If you are measuring positive angles, all these angles that we were working out here were actually positive angles. So if you are moving in that direction, those are positive angles. So if you are moving in the negative direction, those are negative angles. Maybe we're gonna talk about it later, but right now I want you to focus on understanding how to find the principal argument of complex numbers, because whenever you are going to be converting complex numbers to exponential form, converting them to modulus argument form, you need to write them in terms. The angle you are going to use is the principal angle in that case. Now, for instance, this was a number which is actually written in Cartesian form. This is a complex number in Cartesian form. But if you are going to write it in modulus argument form, is going to be z equals to r into cos theta plus I sin theta. That is what you do. But now r is the modulus, which is root 34. So this is root 34. Cosine, the cosine, we are going to use the theta. The theta is the principal argument, which is actually 4.17 plus I sine 4.17. So that's where we are going to use this principal argument whenever we are trying to write a complex number in modulus argument form, or we are trying to write it in any other form like exponential form. So if you are told to write in exponential form, this is actually going to be exponential form is usually written r e to I theta, yeah, where theta is the principal argument. So this is going to be, let me see whether I can be able to write there. If you can be able to see that, this becomes z equals to root 34 e to I. Okay, I can write it. Our principal argument is 4.17 I. 4.17 I. So this is now in exponential form. The most important part is understanding how to find the principal argument.